detector. Okay, so thanks very much for the invitation to speak, and thanks to the organisers for a nice conference. I'm just going to work out which of these buttons makes the... There we go. Okay, so my name is Colin Cotter. I'm from Imperial College, and I'm going to show you some work which is part of this NERC STFC Met-Office Dynamical Core project, which is unofficially named Gung Ho, sort of increasingly officially named. So I'm going to start by explaining what my aim is within that project, and then I'm going to adapt my aim so it's a bit more relevant to this meeting. So the aim, my aim in the project is to contribute to the grids work package, which is trying to identify numerical discretizations for the horizontal. We're just thinking about the horizontal at the moment, the verticals for next year. Discretizations that can be used on pseudo-uniform grids on the sphere. So an example of a pseudo-uniform grid is the one which we just saw, this yin-yang grid, where you don't have any concentration of grid points around the poles. But we want to preserve, as much as possible, all the nice things that the Met Office really likes about the C-grid finite difference method that they already have. So let's change that aim to the aim of the talk, which is to identify numerical discretizations horizontal that are stable and accurate on adaptively refined meshes. So I'm using finite element methods. So although in the project we're looking at icosahedral meshes and things like that, actually everything I'll say can be is completely independent of the mesh. Really, you can choose any triangulation you like. Okay, so let's give you a bit of background from my kind of starting point. So I'm talking about staggered grids. So this is kind of a little bit from near the equator from a latitude-longitude grid, so you can't see any deformation of the squares. So in the horizontal, I think most people know this in here, but the C-grid, the idea is that you store fluxes through edges instead of being, so you store the north-south velocity here and here, and the east-west velocity here and here, and then you store the pressure in the middle. And that's the setup that's currently used. There's been quite a lot of work recently on extending that kind of structure to sort of meshes with arbitrary polygons. So it's the same kind of idea. So the idea is that you store the normal component of the velocity along each edge, and then you store the pressure in the center. And then you can use hexagons. This is a pentagon. This is actually a figure which I stole from this this paper here. And so the real challenge, which was kind of solved in this paper here by John Thuburn, was to in reconstructing the Coriolis. So you've got, if you're just storing the normal component of the velocity, when you want to write down the Coriolis force, that means you've got to be able to compute the tangential component of the velocity at the same place. And the property that you want is that the geostrophically balanced modes need to be steady on the F-plane, so that the geostrophically balanced state doesn't kind of spuriously kind of jiggle around and oscillate. And so that problem was kind of unsolved for a long time with hexagons until, in this paper, John Thuburn worked out how to do this on a hexagonal grid, and then it was extended by John with Todd and Bill and Joe in this paper to kind of arbitrarily structured meshes. And the idea is based on a kind of mimetic kind of structure that you've got in this type of grid. So the idea is that you can evaluate stream function on the vertices of the grid, and then you can take the curl of that stream function to evaluate the velocity by just taking a difference here, and then that velocity you can then compute a flux through all of the boundaries to compute the divergence. And the idea is that if you have a divergence-free, the balance states are divergence-free. And the point about these grids is that they are orthogonal grids. It means that if you take the pressure points, join them together with a line, then the line crosses the grid line at right angles. And it means there's a dual grid which goes around like this, so you can do a little circulation theorem and compute the circulation, and that gives you a vorticity which you can compute at the vertices. And the idea which is described in this paper is that what you need to do is, if you have a divergence-free velocity field, then you need to have a reconstruction of the Coriolis such that when you work out the vorticity, then in the F-plane case, then that vorticity is steady. And so without, I mean, this is a nice paper to read. So without going into too much more detail, it's all based around the what are called the mimetic structures, which means that you can evaluate a gradient and then compute the divergence, and that thing will be exactly zero. Evaluate a curl and then do a divergence, or you can take a gradient and then do a curl of that, and that will also be exactly zero as well. And that's the kind of the basic basis behind the setup. So so that idea was then taken forward by these guys and applied to the nonlinear shallow water equations on kind of arbitrary grids here, and they were able to use that basic idea to build in potential vorticity conservation, so that even though you're storing velocity and pressure as being your kind of prognostic degrees of freedom, there's an implied potential vorticity which is which you can diagnose and which is conserved, and it also stays bounded, etc., etc. So that was a kind of like an added bonus which you could get from that. So we've got into the habit in our group of calling this kind of set of papers TRISC, just to kind of abbreviate that, even though this one is actually RITRIX, but anyway, that's harder to pronounce, so we stick with the abbreviation of that one. So when I talk about TRISC, I'm talking about this kind of this kind of mimetic framework together with this clever idea for doing the reconstruction of the Coriolis. Okay, so what are so now I'm going to talk about some sort of steps which have gone kind of beyond that. So there's one thing we wanted to be able to do was we wanted to remove this orthogonality requirement, which I just showed you here, which is that you need that the pressure points, the line between them, crosses this edge at right angles. So the main reason for doing that was that then we could look at the cube sphere, because the cube sphere, if you have an orthogonal cube sphere, it still is condensing resolution quite a lot near the vertices of the grid, and it also means you can do kind of more kind of extreme kind of adaptive refinements and things like that if you're not confined to this orthogonality kind of requirement. So John and I kind of worked out a kind of framework for doing that. We worked out the conditions that you need to do, but we weren't immediately able to propose an actual scheme which would satisfy those requirements, which is why we've got this word framework in the title. So meanwhile, with Gemma Shipton, my postdoc, we have been done some work where we extended this the idea. Essentially, we did the finite element version of this paper here. So we showed that there are families of finite element methods which, when applied to the linear shallow water equations, are energy conserving. They don't have any spurious pressure modes, and they have steady geostrophic modes. And basically, for the same reason as the TRISC the kind of proofs are pretty much exactly the same, but just kind of cast in a different way. But if you've got finite element methods, then there's a few extra things you can have. So you can increase the order of accuracy if you want within that framework. You can use an orthogonal grid if you want. And the other thing is that you can play around with the balance between velocity and pressure degrees of freedom to remove spurious mode branches. So if you have, if you make a grid that's based on hexagons, and there are spurious Rossby modes, that was kind of analysed in this paper here. So and those branches occur because you've got too many degrees of freedom in velocity compared to pressure. So one of the nice things about the finite element method is that you can mess about with that balance to try to remove the spurious mode branches. So there's quite a few kind of benefits, but this paper was just looking at the kind of the linear equations. So the kind of what I'm going to tell you about in this talk is how to take these finite element methods and apply them to nonlinear shallow water equations and get potential vorticity equation. Okay, so these are the kind of the objectives of the talk. So we've got some kind of target features of finite element formulation that we want to copy. So have a higher order scheme. I mean, it won't just be second order everywhere. Some kind of bounded local conservation of mass, and this conservation of PV, but with a stable advection that's consistent with the mass transport, which means that if PV starts by being constant, then it will stay constant. And then keep this property that you've got steady geostrophic linear modes in the F-plane and that the linear system is energy conserving. So these were amongst the list of properties which we wrote down in the beginning of the kind of gung-ho project. So these are kind of all the things I've built in here. Yes?
So don't we want energy conservation in the non-linear system? I mean, what use is energy conservation in the linear system?
I mean, it's mostly for stability that we know that the system will be more stable if we have that. Yeah. Okay, so what are the properties that we need to import from the Trisk framework into this finite element approach? Well, there are three properties that you need. So one is that you have a discretization of the divergence and the curl, such that if you take a stream function and take its curl to get a velocity field and then take the divergence, then you get 0. So that identity needs to be preserved. That's used in the proofs. And similarly, if you take a gradient of a function and then take the grad perp dot or rot or whatever you want to call it, then that thing is also equal to 0. And then a third property that is required in the proofs is that if you start with a skew gradient of a function, then the Coriolis term maps that into a gradient function. That's the third kind of ingredient that's built in there. So we need to copy all of those things in a finite element framework. I'll show you how that's going to work. So in this kind of Trisk mimetic finite difference framework, feature 1 is obtained by using this grid that I showed you, and then feature 2 is obtained on this dual grid, which I showed you by joining the pressure nodes together and this orthogonal grid. And then feature 3 involves having a clever mapping between the two grids. So it's very much based on this kind of dual grid setup. So in general, the main difference is there's no dual grid in the finite element approach. So I had to find a way to make it work without using a dual grid. So we get around this by building finite element functions that satisfy 1. So we can either have 1 or 2. We can't have both because we've only got one grid. And then we'll get 2 by doing integration by parts on 1, and then use finite element projection for 3. So just as a footnote, John and I are now working out a finite element scheme that does use a dual grid, which is essentially a finite element version of the Trisk scheme. But John's going to talk about that in the workshop in October that's down in Exeter, so you can wait till then to see that one. Okay, so the way that finite element method works is that you have to choose some restriction of your functions, which you're then going to expand in some kind of basis. And these are mixed finite elements, which mean that different types of functions are expanded in different ways. So this is the space where pressure lives, and this is the space where velocity lives, and this is the space where the stream function lives. And the way the setup works is that the stream function space, the functions are all continuous. It's like the classic kind of continuous finite element. And then you've taken a curl, and that means that you're left with functions which only have continuous normals. So you can now have jumps in the tangential component across each of the edges. And then you can take a divergence, and you end up with functions which are completely discontinuous down this end. So each time you take one of these derivatives, you are losing some continuity, which is why I can't have a gradient operator that comes back the other way, because I've already got a discontinuous function. I take the gradient, I've got a jump, so I've got a problem. So that's the kind of general framework. So I choose my functions very carefully, so that if I take the gradient of the curl of a stream function from my collection of stream functions I'm allowed, then that gives me a permissible velocity function. If I then take a divergence of a permissible velocity function, that gives me a permissible pressure function. That's the kind of setup, and that's what is meant by finite element exterior calculus. So you're choosing the spaces very carefully so that this occurs. And there's a nice review, if rather lengthy and technical, in Acta Numerica by these guys here. Okay, so just to give you some concrete examples, because that's a bit kind of fluffy. So this is a very standard example. So if you think of a triangulation, then you could represent your stream function or vorticity or whatever as piecewise quadratic functions, which are fully continuous. And the standard way to do that is to store the vorticity on the nodes and also on the centers of the edges. So you have continuity, quadratic continuity going across each of the edges. If you take a curl of one of those, you get a function which is then linear, because you're differentiated to a quadratic function, so you'll then get a linear velocity field. And it's now only continuous in the normal component. So the way you can store that is you store two normal components on each edge. That's 3 times 2 gives 6, which is enough to store a linear velocity field. And then I can take a divergence of that, because I'm allowed to take divergence of things with continuous normals, and that gives me a piecewise constant function. So this is one example of a finite element space that's permissible. An interesting thing about it is it has the same degree of freedom counts as the hexagonal C grid. So you've got the same number of velocities per cell and pressure per cell, etc., etc. And so therefore it also has extra branches of Rossby modes, which I haven't done any dispersion analysis on to see if they're the same kind of thing as you get in the hexagons or not. Okay, so what I've been playing with is kind of an enrichment of those finite element spaces. So I put a cubic function in the middle of my vorticity space, that's called a bubble function, and then I add 3 extra quadratic functions in the velocity space which have vanishing normals but have kind of tangential degrees of freedom. So there's a jump in the tangential part, so you'll get a different value of the tangential component just on this side. And then you take a divergence on one of these things and you get a linear function which is discontinuous. And if you do the degree of freedom count here, I don't have time to go through it with you now, but you can kind of think about it as an exercise. There's actually twice as many velocity degrees of freedom as pressure degrees of freedom, which is exactly what you have on the latitude-longitude grid if you have quadrilaterals. So that means that you avoid having any, you minimize the chance of having spurious modes at any right. Okay, so that's the kind of finite element space that I've been playing around with in my codes, but this framework that I'm describing you works for any set of spaces which kind of satisfy these rules. Okay, so okay, so I'll just quickly describe how we get the gradient and the curl. We do those by integration by parts. So if I want to take a function here and approximate its gradient, I can't take a strong gradient because there's a jump. So I have to do a weak gradient by integrating by parts. So I take a test function from the velocity space, and I dot, and so I'll define my gradient. So this delta is my discretized approximation to the gradient. So I'll define my approximate gradient as being, I take for any arbitrary velocity test function from this space integrated, that's equal to minus the integral of the divergence of w times d. So I'm allowed to take the divergence of this guy because it's living in this space here. So this is just the integration by parts formula for the gradient. So this is the finite element approximation of this gradient. You can do something similar with the curl. So if I've got a u that's living in this space, I can take a test function from this space and then integrate by parts my curl. So my definition of my kind of finite elementary approximation of my vorticity, what I do is I take my test function and then I take the curl of that test function and dot it with u, and that's just the integration by parts of the curl. And then you can show with a bit of manipulation that I don't have time to really show in detail, if I take my grad and then take my curl, then I end up with getting 0 by integration by parts and showing the divergence of a curl is equal to 0. And so I've got a curl of a gradient being equal to 0, but only in this kind of weak integration by parts definition. So the reason I'm showing you this is because I want to calculate the vorticity, and this is how I get the vorticity. Okay, so I now kind of proceed very similar to how the Trisk paper worked. So I start with my shallow water equations in this particular kind of invariant form. So here I've got the total vorticity multiplied by u perp, and then the gradient. So lots of you know this equation already. And then I've also got my continuity equation for d. Now remember, d is completely discontinuous. So to get for my velocity equation, I dot it with a test function. So here's my test function w, and then I integrate. And then for this term here, I've got a gradient here, so I've got to integrate by parts. So I've got because I'm allowed to take a divergence of w, I'm not allowed to take a gradient of the d part. So that's my u equation. And then the d equation is, d is discontinuous, so I use a discontinuous Galerkin method to discretize the d equation. So now I just do an integral over a single element, multiply by a test function, integrate by parts, and then I've got some flux terms. So this d twiddle is the flux term that you get when you integrate over the boundaries. So this is a sort of continuous finite element discretization for this term and discontinuous finite element discretization for this one. Okay, so how do I get the vorticity equation? So the point is all about the vorticity. So the vorticity is defined, as I showed you before, by taking a test function from the stream function space, the continuous space, and then integrating by parts on the curl. So I have grad perp gamma dot u for the vorticity. So that defines my vorticity. And the thing is that this grad perp gamma is actually an admissible velocity function. So because my grad perp maps from my stream function space to my velocity space, so that means I can actually take minus grad perp gamma as a test function w and substitute w equals minus grad perp gamma into all of these parts here. This term will vanish because div of grad perp is equal to 0. And then I get my approximation to my vorticity equation. So this is just the vorticity equation multiplied by gamma and then integrated over the whole domain. And in the final step, I integrated by parts here, which I'm allowed to do because gamma is continuous, and I will require q to be in the velocity space, which means that I'm allowed to that I can apply the divergence here. Okay, so that's pretty much the entire discretization, except I didn't tell you anything about how to compute this q. So that's the bit that's missing from everything. So the last few slides are just to explain how this q is going to be computed. Okay, so I follow exactly the program of this TRISC papers. So you start by updating D and then diagnosing a mass flux F, and then you write the PV equation as d by dt of q times d plus divergence of F times q equals 0, and then you take the q to be equal to F times q from that PV equation. Then you have a consistent discretization of the PV advection. Okay, so I'm going to have to go very fast here because I'm running out of time. So this is just the discretization of the D equation which I showed you before. You just have to take it for granted from me that a solution of this equation can be recast in this form as a local equation. There's no integrals anymore. This is a pointwise equation. D by dt of D plus divergence of F is equal to 0. This is something that's called flux reconstruction, and you can do that kind of completely locally, so I can work out what this F is independently in each element without having to solve any kind of global elliptic solve. And it still works if I apply a slope limiter to try and control the monoticity in D. So no time to explain that really, but you can ask me about that afterwards. Okay, so now I define a potential vorticity. So my potential vorticity is Q, and Q lives in the stream function space, the continuous space. So Q multiplied by D is equal to curl of U plus F. That's the definition of potential vorticity. So I write that in an integral form. So gamma is a test function from the stream function space. And then for the vorticity, I integrate my gamma by parts, and then here's the test function with F. So that's my definition of the vorticity. And then the PV equation, I can just write down now as being d by dt of this. So this is just now the same equation for PV that I showed you before, but now I've multiplied by a test function and integrated. And you can check that if you have a constant PV, then you can take Q out of this equation, and then you've got d by dt of D plus div F, which is equal to 0, because that's what we fixed before, and therefore dq dt is equal to 0 and Q stays constant. So a constant Q stays constant, just like in the TRISC setup. Okay, and then okay, so here's so now I can integrate by parts in this PV equation because this guy is all continuous and this is continuous normal, so I'm allowed.
You jumped over a really important point there very
sorry.
quickly, which is you said d by dt of qd equals 0, and then the next line says d by dt of q equals 0. So can't you have q change if d change, i.e. have you done anything to control changes in PV due to vortex stretching?
This is d. So, so this d by dt is only hitting this. I think there's something a bit wrong with this slide. What this should say is that gamma times d times dq dt is equal to 0 when integrated, and that's true for all gamma, and therefore dq dt is equal to 0.
Okay.
Sorry, I think there's a mistake on that slide which I can't work out while standing up here.
Okay.
Sorry. Yeah. All right. So so nearly finished in showing you the derivation. So so this is equal to 0, missing equal to 0 here. So this is my PV equation. And then if I substitute in my definition of PV, I can then rewrite it in this form, and then I compare with the velocity equation that I originally had, choosing W equals grad perp minus grad perp gamma, and then I see that all I need to do is take this FQ, and that's my definition of Q. So as long as I construct my Q in this way, then there'll be an implied PV advection, even though I'm actually solving for U and D as being the degrees of freedom. Okay, so don't have much time to tell you about this either. So okay, so one thing about the PV advection here. So the PV is in the continuous finite element space and not in the discontinuous one. And we know that if you just discretize the advection equation in the continuous finite element space, you get wiggles. It's not stable. So you have to stabilize it somehow. So I've been a bit liberal about what I do with PV. So I don't need to be a rigorously bounded method for PV, I believe. I think you just need the advection to be stable and not too oscillatory near to fronts to keep control over the divergence-free component of U. So I just follow the standard continuous Galerkin kind of stabilization approach where I just shove an extra dissipative flux in here. And there are certain ways to do this, which I also don't really have time to tell you about either. So the Petrov-Galerkin method is what I'm using here, which is very closely related to the anticipated PV method. What you do is you replace the test function gamma with gamma plus a upwinding parameter tau times u dot grad gamma. So what you're doing is you're biasing the test function in the upwind direction. And so I shove that into so I replace gamma with this quantity, and then I can rearrange things a bit, and then I just pick up this extra upwinding flux. So this actually stabilizes the advection, but it remains high order. So you still get overshoots near to discontinuities, but it has now made the advection stable. So this is actually something very similar to what Darryl was talking about before, except you've also applied the upwinding in the mass term as well as an advection term. Okay, so I haven't implemented this, but if you really need it, if you really want to remove all of the oscillations near to jumps in the solution, then you can add a bit of extra diffusion, which just switches on near to where there are discontinuities. So this is called discontinuity capturing, and then you just add other extra bits of flux. But I haven't implemented it in the code as yet because I haven't decided whether I need it or not. Okay, so all I'm doing here is I'm modifying this Q in order to kind of stabilize the advection of PV. Okay, so in the remaining 2 minutes, I'll just kind of show you some results, and they're very, very new because I've only had the code working for about 2 weeks. So I hope the next time I show you this stuff, I will have some more results, and we'll be able to do more comparisons with John and Hilary's code and other people as well. So I've adopted a semi-implicit setup, which is actually the same setup as Endgain, the Met Office code. So that's how it's kind of coded up. The Helmholtz equation includes the Coriolis term. It's not really very important. I'm using a slope limiter for the mass transport, and then using this Petrov-Galerkin stabilization for the PV. Okay, so I've only looked at 2 test cases so far. There's this is on the sphere, so we've got the solid rotation test case, which if you don't know what it is, you don't care. It's just a steady state solution on the globe. And these are plots of errors. So here's this is the PV error and the in L infinity and L2, and the U error and the D error, and these all compare pretty well with the calculations which Hilary did. So this is with 11520 degrees of freedom, and then so I did a convergence test. So these are the various errors, and they're all roughly second order. So it's second order error in PV, in U, and in D. And then the next thing I did was started to set up the flow over the mountain test case, and I've realised I've actually set this test case up wrong. So I've set the layer depth to the wrong height, and I think I've put the mountain in the wrong place. But what it does show you, so this is actually a plot of the PV, which I've got as a kind of cartoon, which I can kind of click forward. What it does show you is that the PV is forming filaments, and the thing is staying stable because I've used this Petrov-Galerkin. Oops, I've overshot. So I think there must be some kind of there are definitely overshoots and undershoots occurring, but we have to kind of decide if we care about them. But anyway, I mean, so what I'm showing you is that the model is stable, and it's advecting PV around in a kind of well-behaved way. And watch this space for some results that can actually be compared. So so that's all I have results there. So I'll just quickly give you a summary. So I've adapted this memetic scheme of Trisk to finite element exterior calculus setup. So that means the fact that you've got finite elements means you can use higher order. You don't have to have this orthogonality constraint, and you can tinker with the balance of degrees of freedom to try to control spurious modes. And it's based on having this kind of sequence of spaces for the stream function, velocity, and the pressure, where you take a curl of the stream function to get a velocity, and then you can take a divergence to get a pressure. And you can build in stabilized, consistent PV advection, no problems. And so what's happening now is kind of further test comparisons with other people in the Gung Ho team, so with the Endgame shallow water model and Hillary's code and John's. And John and I are also working on a primal dual grid version, which is kind of like a hybrid between this and what's in the Trisk paper. And I'm now currently working on how to extend this to 3D PV conservation, and I've got some kind of initial formulation for that as well. So that's it.
Go on.
Bob.
Is this stable with vanishing layers? Is it well behaved? If you have incropping?
I wouldn't have thought so, because we haven't got any wetting or drying built in or anything like that.
So you think it's unstable?
Well, I have no reason to expect it to be stable. Why would I expect it to be stable? Is any shallow water stable? It doesn't have wetting and drying?
Oh yeah, you can run with very thin layers. Kind of the Bretherton approach of having massless layers. And Arakawa wrote a number of papers about ways to handle that particular case.
Okay, I guess you can build that in. I don't know. You probably break all the conservation if you do that. But we're not actually planning to use an isopycnal model for the 3D model. So this is just a kind of way to explore the horizontal stuff. So we're going to use a Z coordinate or sigma coordinate for the.
That's a fair question anyway, isn't it?
Yes. The answer is I don't know.
Do you recover the energy conservation from the nonlinear shallow water equations?
You
H squared.
Yes. So but I don't know. I don't think it's useful. So I've got to go all the way back through this animation to slide back. Well, maybe I won't do that. The way to get energy conservation is that you don't put any stabilization into the PV equation, and you have to also, when you do the upwinding in the DG equation, you have to, instead of taking the upwind value, you have to average the value across from either side of the face. And we know that's an unstable scheme for DG. So you can conserve energy, but you'll make nonsense wiggles.
But you will like it, right? Yeah.
But so knowing that is useful from the point of view is that you now know that those are the things that you've switched on, which are now decaying.
Right. No, I could see the stabilization in H would break the energy conservation, but the stabilization for PV shouldn't, because it is energetically neutral, because that cross U dotted with U is 0. The anticipated potential vorticity method does not create or destroy kinetic energy.
Yeah. So what you need is that the Q is proportional to U, and the only way. And so that you get U cross U is equal to 0, and the only way I know to do that at the moment is just to use the standard scheme, which is unstable. So I haven't worked out how to build it, make a stabilization that's conserving energy. I'm also not sure how important that is.
No, you're right. It just depends how big it is.
Yeah. But I know what the sources of energy loss are.
There's a funny story attached to this, which is the Phoenix people actually dropped this element out of the Phoenix framework because it was mildly inconvenient to them. They could not imagine what anyone would possibly use it for. So we had to go back and put it back in. Because
There's a hand at the back.
Yes, you are using function spaces of a different order for different fields, and obviously you do it to avoid null spaces.
Yes.
But I wonder if you can say something about the convergence of the whole thing. I mean, does it, if you want a high order of convergence, second or third order,
Yeah, so
still there, or
Yes, well, so, I mean, so the scheme I'm using, which is this BDFM1, it's overall it's second order. So for what you need to be second order is that all of the function spaces at least contain linear functions. So that means it can represent linear functions exactly.
And that's the case also if it's slightly irregular elements.
Yes, absolutely. That's the whole point of finite element. Yeah.
So you notice in finite volume in the sense that the C grid the C grid has linear velocity and piecewise constant pressure, and the C grid is only second order, subject to some very strong assumptions about things like the rate at which change. So basically, the C grid is only second order due to superconvergence properties.
Yes.
And on a general measure, it's first order. But it's on a general measure, it's first order because it's a piecewise constant scheme.
Yes, it is.
And as soon as you go up, it's still true, right? So if you have linears in all your spaces and you obey the other rules, then you're second order in the general case. And if you're really lucky, you might be higher order if you've got a particularly nice mesh and things cancel. That's a general principle of discretizations.
Yeah, so the framework would allow for higher order elements as well, as long as they satisfy the rules. And in which case, as long as the velocity and the pressure spaces both enclose, for example, all the quadratic functions, then it would be cubic, etc.
Good. Are we done then? I would like to thank all the speakers over the last 3 days. If I wasn't a speaker, I can comment and say that I thought that the quality was overall excellent, and if the next 4 months looks like this, I'm going to be very, very happy to be here. So thank you to all of them.